So there's a couple of smaller topics that are in 8.1 and 8.2. And the first thing we're going to talk about is we're going to talk about domain and range. And this is another idea that keeps coming up through our different units. So the first thing we need are a couple of definitions. So a relation is any set of ordered pairs. And we call it a relation at first because we're not sure whether or not we're going to be able to call it a function. So any set of ordered pairs we have is a relation. When we're looking for domain, we're looking for the set of all first components of those ordered pairs. Or on graphs, we're looking for just generally, this is x values. So your domain is always made up of x values. And we're going to talk about domain, I think in every unit we talk about domain. Range is the set of all second components. More generally, that's our y values. And when we're looking at whether or not something is a function, we're seeing if each first component corresponds to exactly one second component. So what that means is there's no repeated x values. So if I'm looking at, for example, an ordered pair, and in my set I have the pair 2, 4, and then I have the pair 2, 5, I repeated the x value of 2. So we know that's not a function. So when we're looking to see if something's a function, we just want to make sure that whatever our set is doesn't have the same x value twice. And then if you have these printed and you have color, list values only once. So this is where I don't want to see a set that has like the set 2, 2, 2. You only say 2 once in a single set. And you'll see what I mean when we get down to our problems. But this is really important. I do take off for this. When you're writing a set, it should be ideally smallest to largest, and you don't ever put a single number in that set more than once. Once you've said that number's in the set, you don't need to tell me it's in the set again. And the last thing we need, it seems like a lot of stuff. I'll tell you, once we do these problems, these are nice and easy. Is set notation, and this is another thing. These are the two things that people lose points for on these problems. Pretty much the only thing they lose points for. Set notation. When we're looking with, so I say use with points or ordered pairs. Because we're going to do some domain and range where you don't use the sets, the squiggly brackets. But whenever you have a set of ordered pairs, you're looking at just this x, this x, this x, this y, this y, this y. We're going to use set notation, which is the squiggly brackets. Now, you don't need to be an artist drawing your squiggly brackets. So normally it looks like that. But if you can't do that, just make sure the line looks squiggly and not like a parenthesis. And we're good. Just to show me that it's a set. And we use that when we're working with ordered pairs. So our directions here, determine whether each relation is a function, give the domain and range of each relation. So we have a relation, it's just a set of ordered pairs. We know it's a set because it's in the squiggly brackets. So when we're looking for the domain, this is the set of x values. So we're going to make our set, maybe, there we go. We're going to make our set by using a squiggly bracket, and then we're going to list the x values from all of those ordered pairs. So the x values, this is just in case you don't remember, it's x first and then y. So the x values are 3, 5, and 9. And they happen to be in order. That's how you'll see the answers in the back of your book. I'm not picky on that. If you don't get it smallest to largest, I won't take off for that. But generally, smallest to largest. And then the range is the set of all of our y values. So set and all the y values, 4, 8, and 20, and then I'm going to close my set. And notice, within a set, each number is listed only once, which they were only once in this problem anyway. So the last thing we have to determine is function or not a function. And this is all based on the x values. If I look back at my relation, Do I have the same x values in any of my points? No. So this is a function. Since I don't have the x values going to different y values, this is a function. So now we're going to change our set. We've got another set of points. So we know they're a relation. We can't tell for sure yet, or we haven't said for sure if it's a function. So we want to find the domain and the range and determine if it's a function. So for domain, we're just listing our x values as a set. So I'm going to open up my set. The first x value I see in ordered pair is 0. The next x value I see is also 0. Do I need to list it again? No, you've already told me zeros in that set. You don't need to tell me again. That's what I mean by don't write it twice in one set. So the next unique x value is 1 and then 2. Close your set. So even though there's 4 points, there are only 3 distinct x values. You only list the 3 different ones. And then range is y values. So I'm going to open up my set since I'm working with ordered pairs here. I have 3, -2, 6, and 8, which you likely won't see that in a text. And I'm okay if you skip this step. Generally speaking, when you make your sets, you go smallest to largest. And the x values were already in order, the y values weren't. But if you leave them out of order, I'm okay, as long as you put the squiggly brackets and don't repeat values. So our last question, function or not a function? Not a function. Why is this one not a function? Devin. Yeah, which two ordered pairs make this fail being a function? Yeah, this right here makes it not a function because the same x value, 0, goes to 2 different y values. So 0 goes to both 3 and -2. That's what makes it not a function. You can't have the same x value going to 2 different or more y values. Muna. Yes. Yes, it's only the x values that can't map to different y values. Yeah, we'll see this in the next example, actually. Yeah, the y values are okay to repeat. It's only the x values that we worry about in terms of function, not function. Any other questions? And I told you, hopefully this is a nice little break from all the factoring stuff. So last, determine whether it's function, give the domain and range. So domain are all my x values. So I'm going to open up my set. And then I have 3 ordered pairs, and they have 3 different x values. So I'm going to list all of those x values, -3, 1, and 2, and close my set. And then the range is a set of y values. How many numbers are going to be in my range? 2. So there's only, even though there's 3 points, there's only 2 different y values. So I'm going to use the 7 and the 2. Or if you're writing it in order, this one would be easy to do right from the get-go, 2, 7. So the place people lose points on these questions, they have naked sets. They don't put the squiggly brackets around them to show me it's a set. And they would write like 7, 7, 2. I'll take off for the extra 7. You shouldn't have the same value twice in a set. If it's not in order, we can let that fly. But brackets only list those numbers once. And so is this one a function or not a function? This one is a function. Now you see a repeated value. You see that there's 2 y values that are 7, but that doesn't matter. The only thing we care about for whether it's a function or not a function are the x values. I have 3 different x values in the 3 different points, so we know it is a function. So when you're determining function, not a function, look at all of your ordered pairs, see if they all have different x values. If they all have different x values, it's a function. If one of those x values shows up in more than one pair, ordered pair, not a function. Questions? All right, so now we're going to talk about function, not a function with graphs, and then domain and range of graphs. So it's the same concept, but we've got to look at them a little bit differently, particularly with the domain and the range. In order to tell if a graph is a function or not a function, we're going to use what's called the vertical line test. We're going to imagine every possible vertical, so vertical is up and down, every possible vertical line we could draw over the picture of our graph. And what we're trying to do is we're trying to make our graph fail and say, no, this is not a function. And the way the graph fails is if I can find a vertical line somewhere on this graph that when I draw it on over top of my picture, I can get this line to hit the graph more than once. That's going to make it not a function. That means it fails the vertical line test. It's not a function. So for example, on A, I have this circle. So if I drew a line, let's say, I'll do the best I can, right on the edge here. It only hits my graph once, which that means it passes the vertical line test. But I've got to consider every possible vertical line I could draw on this. So I'm going to try another one. I'm just going to move my line over a little bit. Now how many times does that line touch the graph? Twice. It touches it once up here, and it touches it once down here. If it touches more than once, it fails the vertical line test. And when it fails the vertical line test, it's not a function. And that's all because it intersects more than once. So we're trying, and there's a ton of lines you could draw in there that would make it fail. But that's what we're trying to do with graphs, is we're trying to make it fail. We're trying to see, is there a vertical line anywhere on there that I could draw that would hit the graph, intersect the graph more than once? And we can say it fails, and it's not a function. So if I look at B, we're going to become very familiar with that type of graph when we get to Unit 4. It's a graph of a quadratic, which we've been working with a lot. I want to know, is a function or not a function? So can I find any vertical line that when I draw it on there, that would hit more than once? So I could try through the bottom there. Nope, that hits just once. I'm okay. Nope, that hits just once. Hits just once. Hits just once. Any line I try to draw on there is only going to intersect my graph one time. And that's what we want. That's how it passes. Any vertical line will only intersect that graph once. So this graph is a function. So how about C? Function, not a function. Function. It's probably the easiest example to see it's a function. If I draw a vertical line anywhere on here, it only intersects once. Each vertical line will only intersect that graph once. If I can't get it to work to hit more than one point, we know it is a function. And then how about D? Function, not a function. Not a function. Napoleon, what line could I draw on there to make it fail? Yeah, straight line right on the graph. So if I drew, I'm going to have to use a different color. If I drew this vertical line right here, how many points is that hitting? All of them. There's an infinite number of points along there. Is that more than one? Yes, so it's not a function. The only times you really find graphs that are not a function are if you have some sort of figure where it overlaps, so like the circle, or if there is a vertical section. You can have really, really steep graphs that are still functions. It's when it gets perfectly vertical that it fails. So either your graph crosses over itself or you have a vertical area. So those are usually the times that you'll see it being not the function. Questions? Now, domain and range of graphs are a little bit different. So when we were looking at the ordered pairs, we had a list of, these are all of the x values that I see in those pairs, and these are all of the y values. But when I look at a graph, so these are some different graphs here. When I look at a graph, I don't see just this x value, this x value, this x value. Between here and here, for example, there's not just -2, -3, -4. There's also -4.5, -4.6, There's an infinite number of points on that graph. So we're no longer going to use a set. A set is this, 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 and this. When we move to graphs, and we're going to use this idea a lot, we're looking at spans of number. We're saying the graph is between these two numbers and all the points in between. So we're still looking at domain as the x values and range is the y values. That hasn't changed. That's your kind of universal domain and range. But our notation's going to change. So when we're looking at domain and range of a graph, we have these square brackets and we have parentheses. And it's all in whether you include the point you're starting with or ending with or not. So if you use the square brackets, you include the end point. If you use parentheses, you're saying do not include the end point. Now when you're writing one domain and range, you could have a square bracket on one side and a parenthesis on the other. It's based on the individual endpoints. Am I including that number? Am I not including that number? The other thing we need to know, and this is again going to come up in a couple of different units, is we're going to have to use infinity sometimes. If our graph, for example, has an arrow and says that it keeps going and going and going, and we don't have a distinct cutoff point, we say it's either going to infinity if it's going in the positive direction, or negative infinity if it's going in the negative direction. Now, until a couple years ago, I never realized that some people don't know how to write that symbol. So I'd get like, they'd turn their paper, they'd write an 8, and they would turn it back. So to do the infinity symbol, to write the infinity symbol, usually start in the middle, down, up, back, like that. So you start in the middle, this is for your infinities, and draw kind of that sideways 8. Because I'd also get a lot of these, where people just kind of like put the circles next to each other, which is fine. If I can tell you're going for infinity, it's okay. But usually just start in the middle, down, up, and that's your infinity. But whenever you're working with infinity, you always use parentheses. Infinity will always get parentheses because we can never get there. So we're not including it. So for domain, x values, which axis on our graph is x, the horizontal or the vertical? Horizontal. So when we're looking for x values, we're looking left and right because that axis runs left and right. When we're looking for our y values, we're looking up and down because that axis runs up and down. So let's look at these graphs and see if we can find their domain and their range. So let's start with our domain. Now it's not just a distinct set of points, so we're not using the squiggly brackets. We want to set up the graph appears between these two numbers. So in terms of my x-axis, because it's still x values, what is the smallest x value that this graph, not where it crosses necessarily, but is either above or below? So I want to find the left of the graph, which is right here, and see what x value is that over. -5. So that first x value is at -5. Here's the question though, are we including that x value or no? It's something you might have to think back to a previous course, and if you don't know it, that's okay. So why do you say no, Rob?
Because it's an open point.
Open circle. This is the only time we see that open circle, closed circle in this class. But because this is an open circle, it means don't include. So it's an open circle. So we're not including the -5. So the choice then is always square bracket or parenthesis. Which one of those means don't include it? parentheses. So we're going to put a parenthesis around our negative 5. Now we want to see how far over to the right our graph goes. So for domain, we look for the left and we look for the right. And what x value does this graph stop at? What did you say? X value, that's on your y-axis. What's the x value when the y is negative 3? 0. So here's where it stops. I want to line it up with the x value, domain's x values. The x value here is 0. So we're going over to 0. And do we include 0 or no? Yes, why yes? It's a closed circle. So you see when we get to 0, this is a closed circle. That means include the point. And so what's our notation for include? Parenthesis or bracket? Bracket. So what this says to anybody else who's reading your paper is it's the span of numbers. That graph is drawn between these two x values versus when we had the points, we said just this point, this point, this point. We had distinct x and y values. This is setting up a span. It's all of the x values starting at negative 5 but not including and going up to 0. Now we want to look at the range, which is our y values. So when you're looking for your y values, we're always starting with the smallest y values, so you always look down first. So for domain, you look left and right. For range, you look, oops, I guess I got to do it here, down and then up. So I want to find the bottom of this graph. So I'm looking at my graph. I'm going down until I find the bottom of it. And I want to know its y value at the bottom. Negative 3. So the y value down here is negative 3. Range is all y values. Am I including negative 3 or am I not including negative 3? Including it. That's the closed dot. So my notation then is the square bracket. Now I want to look for the top of my graph. So I go down, I go up, here's the top. The y value there is positive 3. Including or not including? Not including. It's that open circle. So like I said, we can do a mix of brackets and parentheses and domains and range, all depending on the one particular point, whether or not I include it. So what this says is the graph goes just from y value of negative 3 up to 3, and it includes every point in between there. It's a span of numbers as opposed to that discrete set of numbers. Questions? Graphs are definitely harder than just points, for sure. Yeah.
Because it's not colored in?
Yes. Okay. Yes, that's what it means by open circle. It's not shaded in the center. Yeah. And you don't include. All right, so let's try the second one. It's a domain. Again, it's that nice curve. It's all connected. So we're going to write a span of x values instead of a set. So what's the x value furthest to the left that this graph covers? Negative 1. Am I including or not including that negative 1? Including. I've got that colored in dot there. So to show we include it, I'm going to do the square bracket, negative 1. And then I want to see how far to the right this graph goes. But by the time I get to the end of my picture, I see that arrow, which tells me it's going to keep going and going. We'll run it into the next graph and going and going. So it's going to go forever in the positive direction, so we're going to draw that infinity symbol. So this is going all the way up to infinity. And whenever you have infinity, you always use parentheses. And now let's find the range, which are still my y values. So the first thing I want to do, now we're looking for the bottom of the graph and then the top of the graph. So I'm going down until I find where the graph ends. And I want to know the y value at this point. 0. It's right on the axis. The y value here is 0. Am I including 0 or not including 0? Including. So we're going to do the square bracket. And now I want to try to find the top of this graph. So it's still going. It's getting taller. It's getting taller. It's getting taller. It's going to continue to get taller as the further out it goes. It still gets taller and taller and taller and taller. So again, it's going to be going to infinity because I can't find the top of that graph because it's going to keep going up as it goes further out. Now, when you look at the last graph, you say, well, it comes from a graph, so we must be using parentheses and brackets. But what is this last graph made up of? Say it loud, Ariana. Just points. So even though it looks like it's a graph, this actually is just like our first problems. Because we use this span of numbers when we have some sort of a curve, some sort of a line that's connected. Because then we're saying it's all of the points from here to here. But this last graph is just a distinct set of points. So the notation we're going to use is not include every number in between these points. Just list your x values. And if it's easier, start by writing out all of the ordered pairs like we had in the first 3 examples. But it's the same idea. I'm going to look first for my domain. But because it's not a curve, it's just points, I'm actually going back to a set because there are only 4 x values that appear on that graph, period. There's 1 x value for each of those points. So I'm going to go back to the set. So use a set when you have just points, whether they're on a graph or written out. You use the parentheses and brackets if you have some sort of a connected curve or some sort of a curve or have a line. So what are the 5, I guess, sorry, I missed the one that was on the axis. What are my 5 different x values? So the furthest one back is at -5. Then I have a -2. There's actually a point on the axis. This is the one I missed too. There's a point right here. What's the x value if it's 0? I'm going to run out of room, so I'm going to just go under it. And then I have 1 and 4. And then the range is again going to be a set. So now I need the y values for each of these points. So this first point, what's the y value here? -2. The second point, what's the y value? -2. The next point, what's the y value? -2. How many times do I need to put that -2 in this set? Just once. So even though there's 5 points, there's only 1 number in my range. So question, would this be a function or not a function? It's a function. The x values don't repeat. Questions? So I do want to talk about the last thing, not the last section, no, it is last, function notation, but let's just take like 30 seconds and like, before we just switch gears. So, who thinks we're going to have school Friday? We better. I agree. We better. We already missed a day. And I'm already short a day because we have like super spring break where we have like the whole week and then the Monday. But in the fall we only miss 3 days. We miss 2 for Thanksgiving and 1 for Labor Day. So I already had to cut out a day. We had 1 snow day already. So let's hope we're here. All right. Let's look at a little function notation, which function notation is actually not the idea of the notation itself, but the idea of the process you could do if you took 081. I used to do these types of problems with 081 students. What gets people in 083 is just the notation. So what function notation is f and then parentheses with x. And what people think that stands for is take f, your function, and multiply it by x. But how we actually read that is you say f of x. All this is telling you what variable comes on the right side. That's all that x does. You're not multiplying by it. It just says what variable you're using in the problem. You're saying I'm taking a function f, the variable I'm going to use is x. That's all that notation means. You read it f of x. And then the types of problems we're going to do here in 8.1, 8.2 says now replace the x with either some number or expression. So my function is f of x equals 4x plus 5. I want you to find f of 1. So this is red, f of 1. All that means is go to your function, and everywhere you had an x, replace it with a 1. So I'm going to take my function, and where I had an x, I'm just going to replace that x with a 1. And then my 081 kids, please excuse my dear Aunt Sally. Go ahead and simplify that. So start with 4 times 1 is 4, plus 5 is 9. So all this is a substitution and simplifying. Don't let the notation trip you up. It's just telling you function f, variable is x. And then these problems are asking you to replace the variable. So in B, I'm looking for f of a minus 1, which means go into your function, and wherever I had an x before, I'm going to replace it with a minus 1. Use parentheses. So I'm going to replace the x with a minus 1. I'm going to copy everything else from my function around it. And then I'm going to simplify. So I'm not just going to get a number here because it's got an a in it. I'm going to have to distribute that 4. So I have 4a minus 4 plus 5. And back to the first day, where we can combine our like terms, is 4a plus 1. So function notation is just an easy way to show replacing. So we still have 5 minutes. We don't get out here till 10. Go ahead and try 2a. So I switched what the function is. Instead of f, the function's g. So g of x equals 2x squared plus 6x minus 9. What I want you to find is g of 3. Not times 3, g of 3. Which means go into your function, and everywhere you have an x, you're going to replace it with a 3. So I want you to replace all of the x's with 3's, and then go ahead and evaluate it. So work it out. Get down to one number here. So what did people get? What did you get for your answers? So a couple 27s. There's usually another answer that pops up. 27, 27. Anybody get anything different? Dennis? 45. Okay, that's the other answer that usually comes up. 27, 45. So let's see. Most likely we agree on this step. Just replace all the x's. And you get partial credit if you do this. Show me what the function notation means. Simplifying. Please excuse my dear Aunt Sally. What's the first thing I need to evaluate? That 3 squared. 3 squared is 9, so it's 2 times 9. So that first term is 18, and then 6 times 3 is also 18. Minus 9 does give me 27. Once you get down to addition subtraction, this is still a problem that comes up a lot in the tests. Don't do the subtraction first necessarily. Once it's addition subtraction, you just work left to right. Addition subtraction, you just work left to right. So it is 27. Now we'll probably not have time to fill in the whole thing, but I just want to make the point with g of 2b that it's the same process even if you have a variable. Even when you have a variable, you substitute the same way. Order of operations hasn't changed. So just like with the number, you start with the exponent. What's 2b quantity squared? 4b squared. So it would be 2 times 4b squared, which is 8b squared, plus 12b minus 9. And don't factor these. Nothing in this chapter 8 has to do with factoring. So we're just, again, creating these expressions. So you see on your homework, I took off a couple of problems.